housekeeping. That's it. If Lali can move to the next slide. Yeah. Okay. So we've got two presentations from Michael Angus and Paula Gozalez from the Met Office. Each presentation about 15-20 minutes. I will have to keep them to time, and we'll follow that by a Q&A section. The question and answers, please post in the question and answer box, and I'll sift through those as we go along. Everyone will be muted, all the attendees will be muted, and the webinar will be recorded as soon as I stop talking, probably, because that's when it starts getting sensible. And the recording will be shared on the Met Office's Science and Services YouTube channel. And if you're having any technical difficulties, don't ask me. There's an email there for use, or use the chat function as well. And if you have any questions about UKCP in general, please look at the UKCP user network email. And we always ask this, please, if you want to speak, have got anything to present on the UK climate projections, how you're using them, what you're using them for, any issues with them that you've found, please do not hesitate to get in touch, because we want to hear about this, and it is your community. I want to share that information around so people can develop the skill sets better, and we can use these data and learn from what's being done for the next generation of UK climate projections. So first of all, I'd like to introduce Michael Angus from the Met Office. Michael is an industry scientist delivering essential weather and climate information to customers, primarily for the water and energy sectors. He's currently working with the water sector, delivering statistical model-based forecasts relating to water demand and weather data to help customers identify peak demand periods. He also helps orchestrate the development and delivery of Assessing Your Climate Risk, an introduction to climate data and reporting training course, which, Michael, if you can say something about that and we have time, that'd be very useful. And this enables external consultants and analysts to confidently use climate data to carry out climate change risk. Michael's on a Met Office academic partnership research advisory panel, working closely with colleagues at the University of Birmingham to develop research opportunities on the theme of hazard to decision making. So Michael, over to you, please.
Great, thanks, David. Yes, so sure, I can say a little bit before I start about that course. So yeah, the Met Office runs Assessing Your Climate Risk course. It's designed if you're looking for doing a climate risk assessment for your own area and you're an external consultant, then yeah, it's a 1 week remote course that we run. There's one in October, although bookings for that fall, and there's another one in February. I didn't expect to be pitching this course, but yeah, if you want to use UKCP for your own climate risk assessment, then I would thoroughly recommend it. Yeah, I should also say that myself and Paula were in the same industry consultancy team here at the Met Office. So she works a lot with energy projects, and I work a lot with water projects, but we also deal with work with other industries, transport, for example, basically looking at solving climate problems and using the climate and weather data the Met Office has available to help businesses adapt for climate change problems, but also weather, any sort of weather forecasting as well. So today I'm going to be talking about how we've been using UKCP to help support the weather sector, particularly for climate impacts, and the role the UKCP 18 projections play in that. And yeah, on the side here are some of the team, past and present, from industry consultancy that have helped to develop this work. So firstly, as an introduction, I just wanted to talk about how the weather influences how much water we use. So on the left here, I'm showing this time series of demand, which is just a measure of the water company's measure of how much water we're all using between industry and home use in megalitres per day. And then the orange line is maximum temperature, and then the dark blue bars here are rainfall. I should say that for confidentiality reasons, all of the X's that have demand information will be blank. I'll get that out the way now because that's going to be in all the graphs, but you can still see the overall trends here, and particularly you can see that during, for example, summer, we have these peaks where the demand really closely matches the maximum temperature, and then we have a few more later in the year, where as temperature increases, the demand follows as well. And so this obviously makes sense when it's warmer. We use more water for activities like watering gardens, washing cars, things like that, and just drinking, obviously. So yeah, higher temperatures, we expect higher demand. But I think this plot on the left also demonstrates that that's not the only factor. We can see obviously that towards the end of the summer, as people's water usage and the population of the region changes, people go on holiday, for example, or return to the region, the demand drops off. So it's not just the weather that influences demand, but obviously it is a big factor. And we can also see here the impact rainfall can have. So there was a very large spike in rainfall during this part of the year, and we saw the demand following that dropped off precipitously. So precipitation also plays a large part as well. And this graph on the right here is just showing that the sort of two-tailed relationship that demand has. So as I've talked about already, the warm weather results in higher demand, but also there are cold events as well, which I won't talk about too much during this talk, mostly because we're looking at future projections of increasing temperature. But when we have these cold events, we have the pipes tend to freeze during very cold winters, and then when it suddenly warms up, pipes thaw and they can burst, and that leads to higher demand through leakage. So that's worth paying attention to, but mostly I'll be looking at these warmer weather events. So that's sort of the weather context, but thinking in terms of climate now. So these are some quotes from the 2021 third climate change risk assessment on water, and particularly from their paper on looking at the risks to public water supplies from reduced water availability. So yeah, stated here that without adaptation and under a central population scenario, there'll be a water deficit across the UK, and that this could rise by the end of the century, equating to the daily water usage between 8 and 20 million people in the UK. And so the estimate is that the magnitude, well, when CCR3 was developed in 2021, the magnitude of risk is generally low for the present day. After the dry spring and summer we've just had, that might be considered as a higher risk at the moment for next year, because that is something water companies are currently concerned about, but rising to medium, potentially high by the 2050s and beyond for most of the UK. So obviously a key component of this is the amount of water storage, but it's also important to consider how our demand is going to change in the future. If there's higher temperatures during the summers, will we see more demand, and will that put more pressure on requirements for the water that we use? Also important from a water sector point of view to consider the regulatory requirements around climate change. So these are some regulatory requirements from Ofwat. It's true that Ofwat is being replaced as an overall the regulatory body for water companies, but at the current moment, Ofwat is the regulator. And so they have these key principles for adapting to climate change around things like providing a transparent pathway of how water companies should adapt to the challenges presented by climate change, and also for our purposes, I guess these 4 and 5 are quite important. Monitoring and reporting and research and innovation is really where the Met Office can come in. I think it's important to highlight as well, just a quote from the Ofwat's Climate Change Principles regulatory report, that they said the use of established scenarios can help companies to assess risk and vulnerabilities. And then they specifically say that in developing plans and pathways, companies should use the representative concentration pathways, or RCPs, adopted by the IPCC and the latest UK climate projection, so UKCP 18. All of which is to say that there's a regulatory requirement for the water companies to consider scenarios, and it's advised that the ones they consider are those within UKCP 18. So in terms of collaboration between the Met Office and the water sector to meet these regulatory requirements, we've undertaken individual projects with both Anglian Water and with Severn Trent Water over recent years. And the goal has been looking at estimating future scenarios of water demand based on these RCPs within UKCP 18. And yeah, truthfully say that the Severn Trent project was nominated for the 2024 Water Awards as well. So looking at how we approach developing these scenarios for the water companies. So I've got sort of a stopgap or a point-by-point approach to the methodology here, and I will go into this figure on point 4 about applying the models to future scenarios. So yeah, the first step here is to calibrate demand model for available customer data. So I'll go into details as we go through the talk about what each of these refer to, but basically the first step is to look at demand data and compare that to recent weather data, and then develop a statistical model where if we have the weather variables, we can predict what the demand would have been on that day. And then steps 2 and 3 here are about applying that historically. So looking at the historical UKCP 18 projections and also observed data, what would the demand have been during that period based on our model? And from that, we can calculate frequency and duration of peak events. So things like defining a threshold. So we looked at multiple thresholds, but in this presentation, we'll be looking at the 90th percentile of demand overall for what peak events are, but then also looking at how many days they occur over, and then also looking at how often those events occur in any given year. And then once we have that for the historical period, and we've really built up a picture of what extreme events look like for demand in the current climate, we can then move on to this fourth step where we apply it to the future climate scenarios. To do that, though, we needed to look at local data. So we need to use the regional, sorry, I shouldn't say local, the regional product, not the local product, but we use the regional 12-kilometer UKCP 18 projections, which are available for RCP 8.5. But we wanted to, because the regulatory requirements also require to look at more of a some of the lower scenarios that don't include as much warming, and to give a general picture of how the projections differ between the scenarios, we wanted to look at the other scenarios as well, 2.6 and 6 for RCP. And so to do this, we used this time slicing approach, which is included in the shown in this graph here, which is essentially to say you find the years for which you have a maximum from 8.5 to the other scenarios. So in this example here, we're showing this box drawn around what in RCP 8.5 is 2040 towards 2060, and the dotted line represents where that would be in RCP 6.0. So yeah, we use this approach to generate a simulation for the other RCPs as well. And then finally, once we have the demand for the future scenarios and for the historical period, we can look at how these the frequency and duration of these peak events have changed or will change based on these projections. So starting on the first point of this method here, looking at calibrating the model for available customer data. What I'm showing here on the bottom is the time series from Severn Trent of their usage, which is just defined as demand minus the leakage that they also record. And as we can see, there's sort of daily variability. You see it wiggles around quite a lot, and that's often related to the weather component, but there's also this long-running trend of an increase in demand. So they're seeing more demand year on year in the area. So this is just another proof that you really need to account for these other factors, not just the weather as well, but some of the base factors here. So to do that, we used a population term within the model, so that stripped out that long running time series. And then this top graph is just showing the relationship between maximum temperature and demand again. And we see that U shape from earlier. So we have these high demand events during warm temperatures, and also the high demand events during colder temperatures. So from that, we can build a statistical model. As it's not the key focus of this talk, I'm not going to go into too many details around what that statistical model looks like. But effectively, we used a generalized additive model, which is split the period 2011 and 2020 into a testing and training data set. For these base terms that I'm talking about, so the non-weather components, we looked at the linear population increase, like I said, and then also the day of the week term. So there's more demand during weekends, for example, and then also a day of the year term to account for things like bank holidays, where we see increases every year. And so this graph at the bottom is showing 1 year of the model. So the orange here is this base term, and these wiggles are the weekly variability. And then the black line is the observed, and the blue line is the modeled. And we can see it's a pretty good fit. There's some points at which it overestimates the demand when there's warmer temperatures. So it's not perfect, but it's doing a pretty good job, and it does a good job representing this higher demand period here, where we had during the year, we had a very warm summer, and demand increased accordingly, and the model's picking that up. And there's some, a scatter plot there and some values at the top about how well the model's performing. But once we have that model, we can then find the impactful events in the current climate, which is quite hard to represent visually, but effectively you take that model and then you have your historical example. So for Anglian, we had a simulation that we'd ran ourselves, and then based on a regional model, and then also modeled demand from historical runs for 1914 to 2018. And so we could find values for demand for each day in this period. And then we looked at things like the frequency, how often peak events occur. We looked at severity of what we looked at a few thresholds of what events look like. And then we also looked at how often we had repeated days of high threshold occurrence. So when we're then applying that to the future thresholds, we have to think in terms of these two kind of questions in that you have to think about. One, how do you keep the threshold? How do you examine the duration and frequency of events, and then how do you examine the critical threshold? So the first method is to keep the threshold for an extreme event the same and look at testing duration frequency. So that's saying we find what's an extreme currently and we see how often that happens in the future. And then the other one is to say, well, we'll keep a threshold of like the 95th percentile the same, but we look at the change in magnitude.
5 minutes.
Thanks, David. Yeah. So to look at what this actually all looks like. So these are some distributions for the 3 different scenarios of the 3 different RCPs. So in each of these distributions, the light blue is the historical, and then the colors are the future projections. And so some key points to make about this really is that in the future projections for all of them, but it's most obvious in these ones at the bottom, and the left is 2041. They're 2 different time periods. The key point is that the distribution flattens and moves to the right. So we're seeing a shift to more high demand events, but also a wider range of events that occur. So both of those are important. So sorry, the left side is 2021 to 2040, and the right 2041 to 2060. So maybe more concrete examples of what that looks like. So looking at a change in the number of events. So here I'm showing a box plot of the number of days per year over a threshold. So the boxes here represent a different range, and then the 3 here are historical observations, and the 3 in the middle are this first 2021 to 2040 period, and the last 3 are 2041 to 2060. So the average in historical observations is around, because it's a threshold of 90th percentile, it's around 35 events per year. And we can see that increases to around 50 events per year, depending on the RCP. So currently, you would expect this sort of event to occur in one every 10 days. It's increasing to more like 1 in every 9 days in the future. One of the big changes we noticed was in the duration of events, so frequency. So this was looking at how many days in a row you had a peak. So yeah, the key thing was in these bottom graphs. So if we looked at how many days you had an event for concurrently in the future compared to the current for the lower values, it didn't change very much. But once we started looking, these bottom graphs are for 11 to 20 days and then 21 to 30, etc. We see this almost double. So what it's saying is, under these different scenarios in the future, your chance of having these longer running events, is almost doubling for compared to the historical period. And then also looking at, sorry, this has changed the duration, but it should be changing magnitude of events. So again, these left panels were observations here, and then these are the different scenarios we looked at first for 2021 to 2040 and 2041 to 2060. And then this is the change in the actual size of the threshold of the threshold exceeded. So it's a change of up to around 2 to 3% higher than the historical, which doesn't sound very much, but that's also including all the base demand that we use every day. So it is, given that this is just the weather term, it is quite a significant change. And we can see that that's, again, fairly consistent across all the different simulations. So to summarize, because I'm aware, hitting where I am with time. So we've worked in collaboration with the water sector to help prepare for the challenge of climate change. And some key conclusions from our work is that we expect to see these peak exceedances occur more often. So we expect more high demand events in the future. We expect the duration on average to be about the same. So there weren't too much difference in the averages, but once we got into the really long events of 11 to 20 days and further on, then there was a real change. And then also we expect the same threshold will equate to high demand. So when we do see a demand event, it'll be of a higher magnitude than it is currently. And I will stop there and skip the next 2 slides and pass over to Paula.
Oh, well, Michael, just a couple of questions first. From,
sorry, we do Q&A first. Sorry, I thought we did Q&A together at the end. Sorry.
Yeah, the first one, I'll read these out on behalf of our colleagues. So first one from Lauren Burton. Has there been or is there likely to be an update to the regulation to use the more recent SSPs rather than the RCPs, or are the RCPs still be used in line with UKCP 18?
As far as I'm aware, the most recent regulations are to use the RCPs in line with UKCP 18. Like I said, right, the regulator is changing, so that might change in the future. But right now, this is still that guidance from Ofwat was from summer 2025. So that's pretty up to date. Yeah.
And then the second question from Alejandro says that you mentioned that water companies are required to use UKCP 18 projections, but these are somewhat outdated. Along similar lines, this question. Given the more recent insights from CMIP 6 and looking ahead to CMIP 7, how much do you think companies might be underestimating their risks by not incorporating these new projections? I suppose this also relates to my feelings about this. If you look at where we are in the climate science, where we are with the state of global climate, where a lot of the new science is indicating, we're at the top edge of the scenario. All the policy commitments made by governments are not going to deliver RCP 2.6 or probably not even 6 in terms of the global temperature change. So, how much important is it to not underestimate the rate of change? So I'm one of life's optimists. Every year I think Liverpool are going to win the Premier League. I've been proved right most of my life. But with climate change, I'm a pessimist. We're not anywhere near hitting the commitments we require to keep it below 1.5. We're not going to hit 1.5. We're probably likely not to hit 2 either. So So we're at this high end of scenarios, and CMIP 7 and CMIP 6 and 7 will indicate the rate of change is increasing as well.
Well, as a Sunderland fan, I would say it's a good job I'm not as pessimistic about climate as I am about football. No, to answer the serious question. So the regulations require companies to use scenarios, and then they suggest that you should do the same as the IPCC and use those scenarios, and they suggest that UKCP 18 meet those criteria. I can completely say, I think in an ideal world, what companies would be looking at things like CMIP 6 and 7. I think UKCP 18 has a lot to offer in terms of accessibility that is difficult for CMIP 6 and 7, but I do take the point that, yeah, those offer a more recent update. In terms of what we've done here, I think because we also used RCP 8.5, right, and that's obviously to be more optimistic about climate, we are below that. So that does give a wider range beyond what is the current warming.
Thank you very much.
Thanks.
Okay, I hope those answer those questions. So now I'll head over to Paula. Paula is a senior scientist with the Met Office with more than 10 years experience using climate information for applied problems in various sectors such as energy, water and agriculture. And Paula's work is mainly focused on the energy sector, in particular projects focused on weather and climate resilience of the energy system, which benefit from her background working in energy meteorology research since 2017. Paula also uses her experience of working on climate variability and predictability to benefit customers from other sectors such as water. So Paula, over to you.
Yes, thanks, David, and thank you, Michael, as well, for the introduction to our team. So the work that I'm going to talk about here was sponsored by the Carbon Trust. It was part of a program that's called the Offshore Wind Accelerator. We worked together for a bit over a year, trying to inform the offshore wind power sector around the North Sea and a bit beyond that. So yes, I'm happy to be talking about that. So I have two very introductory slides here for those that are not very familiar with wind power and for those that are not very familiar with the models. So apologies for those that this is very trivial, but I thought it was good to get to a common ground. So why does climate matter for the wind power resource, right? So it's very obvious, right? There's wind in there. But I think it was important to talk about what aspects of wind matter for wind power, because that might not be that trivial. So there's two components to consider here. One is that wind changes with height. That's my cartoon here on the left. And how it changes also matter for energy production, how turbulent or how laminar the flow is when it reaches the turbine heights. But also, and that's my figure here on the right, the variability of wind matters a lot, because how wind speed is converted to power follows this black line. So that means that it's very non-linear. So there are some specific wind speeds at which it's kind of like the wind power output is ramping, and then it reaches the maximum capacity for generation, and then it drops because of like safety concerns. They need to lock the turbines so that they don't get damaged by strong winds. So how wind changes also matters for the production as well. I'm not including it here, but also wind direction matters a lot. Not so much when we have a single turbine because they can align with the wind direction, but when you have wind farms, they also shade each other. So the predominant wind direction is the one that they are built for, and anything that departs from that is generating less power as well. So that's a very quick introduction to wind power. Then I also wanted to highlight that in this presentation, and like Michael's, I'm going to be talking about general circulation models, so the global component of the UKCP ensemble. And why we are doing that, I think it's important to understand. We are going to describe why in the sense of wind power next, but this is just generally acknowledging that this global climate simulations are really the basis for all the projections that we do into the future, because even when we are using regional climate models and even the local simulations, there's an underlying global simulation that was used to produce them. So they are at the basis of how we project into the future, but it's also important to understand that these GCMs are not perfect, that they are not meant to capture every aspect of the climate system, mainly limited by their resolution, and also that they are subject to a lot of different sources of uncertainty that I'm going to try to discuss as well. So how we get to the point where we see local changes in wind is quite complex, right? There's a lot of processes that interact with one another, and that will lead to changes like here in the middle in the mean wind speed, but also in the how wind changes from 1 hour to the next one, or from one day to the next one, and also changes in things like the wind direction. So when we consider these general circulation models, we're focusing on the information that these external changes in the forcings are giving us into the large-scale patterns of variability. This is thinking about things like the jet stream, the North Atlantic Oscillation, and processes like that affect large-scale climate, but they definitely have an impact on the wind resource as well. We are definitely not going to be covering changes that happen more at the local scale, but in some cases they also reveal interactions with these large-scale patterns as well. So the question now is, how do we use these general circulation models to inform wind power? So this is what we try to do for this project. So the idea is that we are going to be discussing this sample application that we applied over the North Sea, but this is something that could really be applied anywhere else. And these are just a list of different processes that we proposed that we had to follow to make this be robust. So initially, we had to establish a historical baseline. So when we want to look at how things might change, we need to have a baseline. Deciding what's the baseline for a variable for wind is not trivial, because it's quite complex and it's not necessarily measured as well as other variables. But there's also important bits of this baseline establishment, that is, for example, that it has to be quite long. So we need multi-decadal records, because we know that these are variables that have a lot of interannual to decadal variability. So that was important as well. Then the second one has to do with establishing some fidelity test on the GCMs to make sure that they are working as expected over the historical period, and if not, inform how we need to correct them. And finally, the third step is going to be establishing how these simulations are going to be used for the future projections, and how we find robust signals in them. So I'll try to describe all of them in a bit more detail now. So when we, like I was saying, when we try to establish a historical baseline, that's quite a tricky process for example, offshore winds, where we know that there's not a large amount of observational records for these variables, or any really for offshore sites. So we had to make sure that we basically pinpointed anything that we could use in the domain of our interest. Fortunately, we have some long and consistent records that come from existing offshore platforms. And then we also had to resort to some other sites that are not necessarily offshore, but they are quite coastal and remote, so they could give us some more information about other points. When using these offshore sites, it's also important to acknowledge that they might have many features in the time series that are not necessarily going to be captured by models. Like, for example, one of them are wake effects, when the establishment of new wind farms can shade the observations in a point that is downstream. So for dealing with that, what we did was use some statistical methods. In this case, it's called breakpoint analysis, where we find where the shading effects might be affecting this time series, and then what we did was just use them over the period that they hadn't been affected. So all of that was done so that we could establish our baseline, that in our case was the use of the ERA5 reanalysis. What we did was just select a set of these case study sites for which we had observations, and then validate ERA5 for those sites. what we found was that ERA5 performed quite well. It is a dataset that is widely used for energy applications. And in particular, we had the expectation that for offshore sites, it was going to behave a lot better than over land, where we know that has some biases. But we found that it was generally working quite okay. You can see, for example, that through these wind rows, it was even capturing the dominant wind directions quite well. But there were some biases, so we decided that it would still be a good idea to bias correct ERA5. So that's what ended up being our baseline. We took this ERA5 reanalysis for the period 1959 to 2022. From ERA5, we have the advantage that we have wind at two heights. We have 10 meters and we have 100 meters that is closer to the hub heights of wind turbines. And how we corrected it was using another data set that is called the New European Wind Atlas. These are the result of mesoscale and even microscale simulations that are created to understand the wind resource better. This one in particular is produced by DTU, and what it gave us was a much better knowledge of the wind climate for each grid point. So we used that to correct ERA5. The advantage of still using ERA5 is that it has a much longer record, which we knew we needed to characterize the variability. So the bias wasn't really important. It was around the order of like 2% in the mean wind speeds for the offshore locations. So I think this is where it gets more relevant to this webinar. This is how we ended up using the GCMs. So what you'll see here is that, like I was saying, our baseline ensemble is the UKCP global, right? But because we knew that for the large-scale projections, there's a lot of uncertainty that is coming from the models themselves, we also complemented it with a set of 7 it's called the CMIP 513 subset of CMIP 5 models that was selected to complement the global simulations. So in the end, we end up with a bit of a larger ensemble, but that is meant to also capture this multi-model uncertainty. So as I was saying, we have this need to look at wind at height. So what we did there, one of the post-processing bits of our analysis was to convert from 10 meters to 100-meter winds, because the UKCP 18 models only have 10 meters. So we did that by statistically learning the relationship that we saw in ERA5 and then applying those models to UKCP 18. In that case, we did it for the zonal and meridional components of the wind separately, because we were also intending to look at changes in wind direction, so we wanted to preserve that. And then the second step of our post-processing had to do with applying some bias corrections to the ensemble, which we did based on this improved version of ERA5 that we had created. So once we completed that, we basically just looked at how the models were performing over the historical trends and variability, and then looked at the bias-corrected projections. So yeah, the points I wanted to highlight are that by including this complementary ensemble of CMIP 5 simulations, we are able to cover both the model uncertainty part, but then also the scenario uncertainty part, which we knew it was important to consider as well. So again, the evaluation of the GCMs over the historical period, we did both at the points of our case study sites, and then also in terms of the larger scale patterns of trends and variability. This is just showing one of the cases where we see that if we use the uncorrected version of the models, we were seeing some biases, for example, in the distributions of wind speeds, which we discussed that it's important in terms of how much power output we get at the other end. But after correcting that, we kind of like solve those problems over the historical period. The same happens with the overall seasonality of the variability as well. The wind directions wasn't really that bad to begin with, and it's not massively affected by the correction. So when we go to evaluate that, I think it's important to establish some kind of parameters. So in the top here, we are showing basically some trends in the wind speed for the different seasons of the year. When we, in these cases, use a thick line, what that is saying is that those changes are statistically significant. When we establish significance in the models, we do that by looking at robustness across the ensemble. So we look at different percentages of agreement in design between the models. And what we can see just right away, I'm not going to discuss the details the changes in detail, is that in general, the picture is quite varied. We see that it changes a lot from season and from region to region. So what we did was just highlight some specific hotspot areas where we were observing, specific changes that were a bit more robust, but also some areas that we knew were of specific interest to the industry, like, for example, the whole of the North Sea, because it is highly exploited and likely to continue to be exploited in the future. So for this evaluation, what we decided to do was also to think about ways in which we could condense and make this information a bit friendlier for the users. So we ended up creating these simplified plots that highlighted for each of these hotspot areas that we had pinpointed what the historical trends in mean wind speed and in variability, and also in mean wind power and wind power variability were telling us. And again, highlighting where the changes were significant or not, and where they were robust or not for the models. Another important thing that was a key result of our analysis was that in many of these regions, the decadal variability dominates over any trends that were observed over the historical period. So that was also something that we wanted to highlight. This is something that is very in a cartoonish way exemplified here on the bottom left. Some sites, they could have a very strong trend. In this case, I'm just exhibiting a downward trend. But in some other cases, we see a lot of these wiggles around that trend. So for any specific decade that we are analyzing, it could be that we see the opposite changes. Like we could be seeing a positive trend, but that's not really the climate change signal of the site, and it's just being overshadowed by that internal variability. So that's what's highlighted by these blue bubbles in the plots. Those are areas where the interannual to decadal variability was larger than 10% of the long-term mean of the site, and that meant that that was overshadowing any of the trends that had been shown over the historical period. When looking at the future projections, things get a little bit more complex because we are analyzing different periods into the future. So we looked at the near future and the far future in a similar way that Michael was showing with the water demand analysis. And at the same time, to also consider the model component of uncertainty and the scenario uncertainty, we had a split, right? So we have the UKCP 18 PPE for the two scenarios, 2.6 and 8.5, and then we also have the complementary CMIP 5 models at the end. So the idea is again to look at this in a seasonal way, but also to pay special attention to these hotspot areas that we had identified previously. And what we see is that in general, there's a good level of agreement in the projections for most of these regions that we paid attention to. But there are specific seasons where the uncertainty is quite large, in particular the winter, which is a key season for the sector because there's a lot stronger winds in the area. So it's when they get the most of their production. The projections don't really agree so much, and it depends on the scenario and the specific period that we are looking at. So again, for our customers, we try to summarize that, producing the same sort of figures. So here, this is referring to, so when we have these full arrows, it means that the results tend to agree, and that means that they agree in terms of they are robust across the ensembles, but also relatively independent of the period of the future. But as you can see, in terms of like the magnitudes, we cannot really give them, very specific projections because the uncertainty is quite large. In general, what we are seeing is that they tend to be small. They tend to be smaller than 10% of the baselines of the long-term climate. So it means that in general they also are smaller than the range of natural variability for the sites. But we see, for example, that over the summer season, the agreement is quite high for general decreases in the wind resource. So I think just getting to the end, I think the bits that I wanted to highlight from our presentation was that we see that the climate variability of this area is quite large, and it can tend to offset these long-term trends. So that's something that is important for the industry to acknowledge, because in their own resource assessments, they need to make sure that they include very long time series to make sure that they understand what are these extreme values that they can get in terms of their production. So this idea of generating long-term records is equally as important as looking at the future projections. And we've shown that despite their reduced resolution, these global models are quite useful also in understanding the impact of the changes in these large-scale signals into the resource of the sites. We also want to highlight that these post-processing steps are quite critical to make sure that the data is turned into something that is very applicable to this specific application. And finally, that we don't undermine the different sources of uncertainty. So as in many cases, we see that this tendency to use the UKCP 18, which we think it's great, but it's also important to acknowledge that it might be smart to complement the analysis of UKCP 18 with other subsets. In my case, it was some CMIP simulations, but in the case, for example, of the regional simulations, we also have access to the Eurocordex UK, which represents the multimodal component of the projections as well. So it's important to highlight that. And that's it. Thanks, David.
Paula, thank you very much. We've got a couple of questions, both initially from Sitlali, but if anyone else has any questions, please do put those on the Q&A. So first one from Sitlali, and I like this one. She does thank you for the talk. How many bias corrections did you try before settling with the one you used? And I'd like to add, why did you use the one you used?
So I'm going to be very honest. It was a quite short project, so we didn't have a lot of time to explore. We had to be quite pragmatic here. And like I said, we were quite fortunate in finding out that we didn't really need very massive bias correction because over the ocean, RFI was performing quite well. What we did was just apply a correction to the mean and the standard deviation. So it's a stat. I think we might have done it at the seasonal scale, right? So each month, correct each month independently. But that was all we had to do. We didn't have a strong need to go to say a quantile correction of wind. But at the same time, at that point, the newer wind atlas, which we used to correct with, was only providing long-term statistics. It wasn't providing time series of wind for the sites. So we were quite limited in what we could use. It's not like we could have done so I think we only had access to the mean wind speed, the standard deviation, the maximum and the minimum as long-term fields. So that was all we had to correct.
So what, just going on to those wind data sets, then, what would be the ideal wind data set that you'd require?
That's a great question, and I think
that's a surprise for me.
That's so we definitely need high resolution hindcasts for this. It's tricky, right, in the sense that these are large data sets, and we are talking about the need to have sub-daily time series for these variables so that they are applicable for energy, but I'm sure it's also for other sectors as well. For example, in terms of the support to infrastructure that we do, we also know that in terms of like wind damage, having information about wind gusts is also quite important. These atlases are great, and they are tending towards that. Now, the newer reanalysis is providing some information on time series, so you have something like 20-something years of time series for I think it's at 30-minute frequency, right, for quite a high resolution area over the whole of Europe. But the limitation in that is that this is just providing wind. So for some other applications, right, it's not going to be enough, right? So we think that this idea of developing these high resolution hindcasts to complement the UKCP, hopefully that's something that could happen within the UKCI as a new project, would be very ideal for this sort of applications. I'm sure Michael can agree that it could be useful for water as well.
And just a follow on in terms of the types of energy, so you look at offshore wind. Have you had any inquiries about looking at offshore wave power?
So we haven't in particular, but our larger team has a marine applications sub-team as well, and they work a lot more with wave. I think most of their work so far has been on the forecast side of things, but it's very much related because one of the big challenges that they have is the operation of these offshore sites, and these weather windows in which they can go and service the different offshore platforms. So that is something that is quite important, and I'm sure that understanding any climate trends into these weather windows is also something that they're quite keen to understand.
And just another follow-up from Sitlali as well. How do you choose a historical period to make sure you're looking past the local variations? The waves are, well, in here, the waves in inverted commas around the main trend. So how do you know you're now looking at the trend you're interested in?
So I think the key there is just have as long as a period as you can. And then there's information that you can use, like different statistical processes that would help you untangle the long-term trends from any other source of variability. So, I mean, it could be something as simple as detrending that very long time series and then looking at what's left. But there's more complex and perhaps even more robust methods that can be used, like, for example, finding a regression model between the global mean temperature and your time series. So that perhaps tell you more about the attributing it to climate change, right? The idea is that whatever trend we are seeing in global mean temperature is mainly driven by climate change. So trying to understand how much of that is related to the long-term changes that you see in wind.
Okay. Michael, I've just seen you come on, so I just presume you're following up the point that Paula raised that you may be able to cover.
No, I just just in case there's anything I need to
okay.
okay. But no, I'm fine. I didn't want to come in. Thank you.
Okay, no worries. Okay. Look, I'd like to pass my sincere thanks on to Paula and Michael for their talks. So thank you very, very much. And I hope that's picked up questions and points. And please, if you've got any follow-up, please do get in touch with the UKCP user network. Email that's down at the bottom of the slide. The next webinar is on the 23rd of October, again at 12 o'clock. This will be Laura Dawkins from the Met Office, which will be looking at integrating UK climate projections with spatial risk frameworks to inform government policy on climate resilience. So very much looking forward to that one. And again, as with most of these talks, this is have a technical tone, but it's not a technically detailed talk. And this should be of interest, especially around government policy to all end users of the data, and also how that fits in with the wider application of scenarios and climate data into delivering resilience and adaptation strategy for the UK. So, Paul and Michael, thank you very much. I'd also like to thank Sitlali for pulling this all together. Without whom help and assistance and everything, this wouldn't really happen. So thank you very much, everyone, and thank you very much for attending.
Thanks for having us and for organizing.
Thank you very much.
Bye-bye.
Bye-bye.